First of all, I'd like to thank the organizers for giving me an opportunity to speak here. I'm going to talk about the theta JT gravity and double-scale SYK model. My talk is not really directly related to the integrability or process parameters, but I hope some of you might find this interesting. So this is the plan of my talk. After a brief introduction and motivation, I'll explain double-scale SYK model. Many of you are not so familiar with this, so I'll explain first. And then I'll move on to the matrix model for this DSSYK, which is called the ETH matrix model. And I'll argue that after taking a double scaling limit of this matrix model, the theta JT gravity appears from this model. Okay. So the holography in the theta space is not so well understood. So it is highly desirable to have a very simple and tractable example of the theta quantum gravity. And it turns out that two-dimensional JT gravity with a positive cosmological constant is a very useful time model to study this problem. We have already heard about three-dimensional theta gravity in the previous talk.
Sorry,
okay.
Could you push your mic a bit higher?
Higher. Okay.
Yeah, that looks better. I think that's good.
Is that good?
Yeah.
Okay. So we have already heard about the three-dimensional version of the theta quantum gravity in the previous talk by Muehlmann. But in my case, I would consider the two-dimensional version of the theta JT gravity, which might be simpler than the three-dimensional case, I guess. So in the case of the ADS version of the JT gravity, the holography is quite well understood. And the ADS version of the theta gravity, JT gravity is dual to SYK model at low energy. And this duality, holography, comes from the fact that these two models are described by the same mode called the Schwarzian mode. So they share the same degrees of freedom. So they are naturally dual to each other in a holographic sense. But if you go to the higher genus, or including the higher topology, this duality can be promoted to a duality between JT gravity and some double scaling limit of random matrix model shown by SYK Stanford in 2019. So it turns out that this JT gravity matrix model of SYK Stanford can be embedded into a finite dimensional matrix model called the ATH matrix model. And this is the genus 0 eigenvalue density of this ATH matrix model. It has a finite support and two edges. And if you focus on the lower edge, low energy side of the spectrum, we recover the ADS version of the JT gravity of SYK Stanford. And my proposal is if you focus on the upper edge, or the high energy side of the spectrum, it corresponds to the theta JT gravity. This identification was already suggested by these people based on bulk semi-classical picture of sine dilaton gravity. But what I did is take a double scaling limit of this matrix model directly around this upper edge and recover this theta version of JT gravity. Okay. So basically, this slide is the one slide summary of my talk. So this is the takeaway message of my talk. So if you take a scaling limiter on the upper edge, you get the digital space. Okay. So let me briefly explain double scale SYK model. Maybe the audience here are not so familiar with this model, so I'll talk about this model in a couple of slides. So the SYK model is a very interesting toy model for holography, proposed by, as a model of holography is proposed by Kitaev in 2015, 10 years ago. And this model is a system of n major fermions with this Hamiltonian, given by this Hamiltonian, where J is the p-body interaction coupling, which is a random coupling with Gaussian distribution. Okay. So the Gaussian nature of this random coupling is just an assumption, but which this Gaussian assumption simplifies the computation a lot. So this serves as a very tractable toy model for holography. So this Gaussian is just an assumption, which makes life easier. Okay. So Barkus and company showed that this SYK model can be exactly solvable by taking certain limit. This is called the double scale SYK model. And this limit is a large n limit, where n is the number of flavors of major fermions. And at the same time, we take large p limit, where p is the number of p-body interaction in the Hamiltonian, in such a way that p goes like a square root of n. Well, in other words, we take n and p both large with p squared over n fixed. And this combination is called lambda. And this limit is called the double scale SYK. Okay. So another thing about this limit is that if you compute the moment of the Hamiltonian, trace h to some power, and take the average of the random coupling, this moment, computation of the moment, reduces to some counting problem, combinatorial problem of the intersection number of chord diagrams. So we count the intersection of chord diagrams with weighting factor Q is given by the minus e to the minus lambda. Lambda is p squared over n. Okay. So here is the example of the chord diagram. In this example, I'm considering trace h to the 8th power, 8 Hamiltonian insertions. So we take a trace, so we draw a circle, and we put 8 Hamiltonians around the circle, and take the average of the random coupling. Can be computed by the weak contraction, because we assumed this random coupling is Gaussian. So the average of the random coupling can be computed by the weak contraction. And for each weak contraction, we draw a line called chord in this business. And this is here the example of some chord diagrams coming from the weak contraction of the random coupling. And then we count the intersection numbers of this diagram. In this case, we have 2 intersections, of course, here. So this diagram comes with a factor of Q squared. And because we are taking the average of the Gaussian random variable, we have to sum over all possible weak contractions. And as a diagram, we draw all possible chord diagrams and count the intersection numbers and sum over all. Okay. And this is just a combinatorial problem. So, and if you look at the math literature, this problem has been studied by mathematicians a long time ago, and it has been solved. But for physicists, it's easier to introduce some transfer matrix. And it turns out this combinatoric circle diagrams can be solved by introducing the transfer matrix given by this. And here A plus and A minus are Q oscillator, which creates or annihilates the chords. Here N is the number of chords, it represents the number of chords. And if you act A plus, N increase by 1. And if you act A minus, N decrease by 1 with some Q-dependent factor here. And the E naught, sorry. So here E naught is depends on some normalization of the random coupling, which comes from the variance or the width of the Gaussian distribution of the random coupling. So this is some overall normalization which is related to the distribution of the random coupling. And this transfer matrix can be diagonalized in some basis parameterized by the variable theta, which is some angular variable. And the eigenvalue is given by, let's get the cosine of theta. Okay. And this eigenbasis and the overlap of this eigenbasis and the original chord number state is given by the Q-Hermite polynomial, like this. And so this problem has something to do with the Q deformation of polynomials and so on. And using this kind of machinery, you can compute the disk amplitude of the SYK like this. So for the partition function, is given by this expression. It exponentiates the transfer matrix sandwich between the vacuum of the Q oscillator. And this has a nice integral representation in terms of the parameter theta, angular parameter theta. And this exponent is just the eigenvalue of this transfer matrix in cosine of theta. And here, the mu of theta is some measure factor given by this infinite product expression, the Q Okuyama symbol. And this measure naturally arises because this orthogonalized, the Q-Hermite becomes orthogonal with respect to this measure. So this is a very, very brief review of the SYK. Okay. Then I'll move on to the matrix model of the SYK. We can construct some Hermitian matrix, one matrix model in such a way that this matrix model reproduces the known disk amplitude of the SYK in the large L limit, where L is identified as the dimension of the Hilbert space of n Majorana fermions, dimension of the Hilbert space of SYK model, 2 to the n over 2. And by matching the measure, mu of theta, and disk genus zero eigenvalue density of this Hermitian matrix model, we can fix the form of the potential like this, given by some series in infinite series of Chebyshev polynomial with some Q-dependent coefficient. And So this matrix model is called ETH matrix model. The ETH stands for eigenvalue thermalization hypothesis. So what we did is basically replaced the original SYK Hamiltonian by a random matrix. But of course, the SYK Hamiltonian is not a random matrix. It's a system of fermions with random coupling. But this replacement can be justified by appealing to the eigenvalue thermalization hypothesis, which basically says that some universal feature of the Hamiltonian, some random Hamiltonian system, such as the eigenvalue statistics, eigenvalue correlation, can be captured by some random matrix. So that's basically eigenvalue thermalization hypothesis tells us. So this is why this model is called ETH matrix model. Okay. So we just switch gears to consider the matrix model, which is was constructed by matching the SYK at the genus 0. So we are interested in some large L expansion of some correlator in this matrix model. More specifically, we consider the connected correlator of the partition function, trace e to the minus beta h, but h is now becomes a random matrix with some specific potential, which I showed you in the previous slide. And it turns out this correlator has a nice large L expansion with using some basic building blocks. The one ingredient is called trumpet, which is given by this form, where I is just a modified Bessel function, I Bessel function, which is called trumpet. Another important ingredient building block is the so-called discrete volume of the moduli space of Riemann surfaces, okay, which depends on the n length and some n integers. Then we sum over all small b. If you're familiar with JT gravity story of SYK Stanford, this is almost looks almost similar to the JT gravity amplitude. So in that case, we have also a trumpet and the volume for the moduli space. But in the case of JT, this small b is a continuous variable, and we have to integrate over 0 to infinity. But in the case of this ETH matrix model, this integral is replaced by the sum, discrete sum. And so this volume can be computed by the method machinery of topological recursion, and I have computed for first few terms of this volume. And, okay, so let's consider the double scaling limit of the ETH matrix model. So by construction, if we focus on the low energy side of the edge of this ETH matrix model, this reproduces the matrix model of SYK Stanford. And indeed, we can check that the measure factor goes to sinh of square root e, which is known density of states of the Schwarzschild theory. So this is just a check at the genus 0, but we can go to the higher genus check by taking the discrete volume of this ETH matrix model, I can show that this, in this double scalar limit, this discrete volume goes to the Wavy-Peterson volume, which appears in the JT gravity amplitude. So the lower edge corresponds to the ADS version of the JT gravity, as expected. So natural question is, what happens if you take the limit around the upper edge or the high energy side? Of course, I have already told you the answer. It corresponds to the theta version of the JT. But to discuss this problem, I have to stress that lower edge and upper edge are not quite equivalent. At the level of the eigenvalue distribution, they look almost identical. So because the matrix of the potential is an even function of the matrix, so if you change the sign of the matrix, it doesn't change the form of the distribution. But we should remember that we are computing the correlator of this partition function. And this quantity, literally c to the minus beta h, is not invariant under sign change of the matrix. So the insertion of this operator into this matrix model breaks the symmetry of h goes to minus h, so they become distinct. So as I said before already, so double scaling limit, if you take the double scaling limit around the upper edge, we get the theta version of the JT gravity, which has been studied already by Maracena, Triachi Yang, and Kotora Jensen. But if you look at this quantity more carefully, if you change the sign of beta and h simultaneously, this becomes invariant. So in some sense, the theta JT, or the scaling limit around the upper edge, is basically given by the analytic continuation of the ADS version of the JT gravity by sending beta to minus beta. But it turns out this analytic continuation is quite subtle. So we have to be very careful to define this analytic continuation. And the subtlety comes from the fact that if you look at the spectrum, E of theta as a function of theta, the angular variable, it looks like this. And this spectrum serves as a potential for the variable theta. And the theta equals 0 corresponds to the minimum, and it corresponds to the ADS version of the JT gravity. But if you focus on the upper edge corresponding to the theta equal to pi, you can clearly see that this is maximum, and this mode is tachyonic, becomes tachyonic. So you have to be careful how to define this integral over the variable theta. So if you naively expand around the theta equal to pi or the upper edge, we get a wrong sign Gaussian integral because it's a tachyonic. So to make this integral convergent, we have to rotate the integration contour to the imaginary direction. And it turns out this integration deformation or rotation of the integration contour precisely reproduces the prescription proposed by Kotora Jensen for the theta JT gravity. Their prescription basically says that we have to put a factor of I to the genus counting parameter. So basically, the genus counting parameter for the Sitter case becomes a pure imaginary I times some real number. And it turns out this I in the genus counting parameter comes from this subtle change of integration contour. Okay. So we can also argue that semi-classical bulk picture of this JT, of the Sitter JT gravity. So we can argue at the level of classical solution that the bulk metric corresponding to the upper edge is given by the minus of the metric of Euclidean edge2. So in other words, the bulk metric for the upper edge is a minus signature, has a minus signature, which is denoted by minus ADS2. And because of the very strange feature of two-dimensional metric, it turns out this minus of the metric of ADS2 has a positive curvature, so it can be interpreted as the Sitter space. So that's why the upper edge corresponds to the Sitter. Okay. And using this kind of technology, you can compute, in principle, we can compute various quantities of interest in cosmology, like Hartree-Hawking wave function of the Sitter space. And Hartree-Hawking wave function is given by the expectation value of the trace of E2 minus ILH. So beta, if you take the beta to be pure imaginary, this corresponds to Hartree-Hawking wave function. And L specify the size of the symptotic feature of the Sitter space. And we can check that the matrix model result reproduces the result of Marutsuna-Toriyachi Yang. Okay. Maybe my talk was a little bit too fast, but this is the last slide of my talk. So this is basically the summary of my talk. So the South-Shenka Stanford matrix model can be embedded into a finite size matrix model called ETH matrix model. And if you take a double scaling limit around the lower edge, we recover the South-Shenka Stanford result. But if we focus on the upper edge, you get the Sitter version of JT gravity. So as a future direction, it's very interesting to include the matter operator into this story. So as discussed by these authors, if you include a matter operator, this matrix model becomes a two-matrix model. One matrix for the Hamiltonian and other matrix for the matter operator. So it would be very interesting to compute the cosmological correlator of the matter operator in the Sitter JT background using this matrix model technology by taking a double scaling limit around this upper edge. So I'll stop here. Thank you.
So you said like if you double scale at the lower edge, you get the usual JT matrix model, and then you get the Weil-Peterson volume, and then the trumpet for the JT matrix model.
Right.
And what happens if you do the double scale limit in the upper edge? You get the same Weil-Peterson volume, or?
Yeah, same one. Yeah, same Weil-Peterson volume.
Exactly the same.
Exactly the same. Yeah.
And then trumpet is different, I guess.
Trumpet becomes different. Yes, trumpet trumpet carries some factor of I.
Mm-hmm. Okay, thank you.
One problem that was pointed out by Kotler and Jensen, if you make the string coupling imaginary, then the non-perturbative effects become order 1. They become very large. Do you understand, because you come from finite n, how we should think about the non-perturbative completion of this model?
So before taking a double scaling limit, everything is becomes finite, because you can go to the finite n. I don't clearly understand how non-perturbative effects in the Doshita case arises in this whole picture of this. I don't know the answer.
Is it fair to say that you would say that DS2 alone is not consistent, but at the non-perturbative level you have to have both DS2 and ADS2 coexistent?
Yeah, that might be the case. Yeah, but I'm not sure.
Okay, thanks.
Thank you. Very naive question. So when you presented the chord problem, then its solution is given by the finite n Gaussian integral, yes?
Chord problem?
Yes, the number of chords with a given number of intersections. This is the coefficient in one of the in the 1/n expansion of the partition of the free energy of the Gaussian model.
Not really. It depends on we have a very general definition. It comes with a weight of Q. It depends on the parameter Q.
1/n or 1/n squared, this Q parameter.
Q parameter is given by the e to the p square over n.
Well, maybe we can discuss.
Oh, okay.
After the
I also have a question.
Oh.
What is the matrix model description of two coupled SYK models?
Two coupled SYK. You can consider the double trace correlator like this. So, and set the random coupling equal for both systems. Then we consider the double trace correlator like this.
But so the interaction between the two models were the common.
So you take so you set both the random coupling same on both two systems, then they start to couple each other. But if you completely set the random coupling completely different, this is just decoupled, factorized.